Picture a simple theoretical planet. Simpler. Even simpler. Okay, maybe not that simple. That planet is called Daisyworld, a model created by James Lovelock and Andrew Watson. Daisyworld itself is an imaginary planet that is composed of two regions, patches of white daisies and patches of gray soil. Now, the temperature of the planet is heavily determined by the amount of daisy coverage. For instance, white daisies reflect more energy back out to space, while on the other hand, patches of soil tend to absorb more energy from incoming solar radiation from the sun. We call this amount of reflectivity albedo. Albedo can be described as the amount of incoming sunlight that is reflected back into space and is usually denoted by a number between 0 and 1. The more reflective an object is, the higher its albedo, and vice versa. For example, an object that is perfectly reflecting would have an albedo of 1 as it reflects all incoming solar radiation, whereas if we had a completely black object, it would have an albedo of 0, indicating that all incoming light is being absorbed. Going back to Daisyworld, changes in the population of daisies will serve to regulate the planet's temperature, either by resisting or amplifying the warming of the sun's solar radiation. If the population of white daisies increase, they reflect more solar energy, ultimately increasing Daisyworld's albedo to cool the planet. The increase in albedo as a result of an increase in daisy coverage is referred to as a positive coupling, as denoted by the arrow, which occurs when a change in one component's property results in a change of another component's property in the same direction. The opposite of this is called a negative coupling, as denoted by the line and circle, which occurs when a change in one component's property indirectly changes the property of another component in the opposite direction, which we can see when the surface temperature decreases as albedo increases.